Center of mass of a thin uniform rod. Let us consider a thin rod whose width that is if it is in case the cross section of the rod is rectangle, or will take radius in case the cross section of the rod is cylindrical. So if the either radius or the width of the rod is much smaller than its length, so taking the origin to be at the geometrical center of the rod and x-axis to be along the length of the rod at x, so there is an element of same mass dm located at minus x. We have taken here, you can see that this is the origin and this is a thin rod. That means the radius of the rod is very small in comparison to the length of the rod. In such situation, if we are taking any element, because this is suppose the total length of the rod is L, so in such situation you will see that it is divided into L by 2 here, and this is also L by 2. I can write minus L by 2 here since it is negative side of the rod. So in such situation we have taken here an element. This is the element, a small element dm of the rod, which is x distance from the this origin. So you will find another element dm of the same mass in the distance minus x. That means in such situation the net contribution of every such pair of the integral, and hence the integral del x dm equal to 0, because every pair is having the same mass in the same distance but either side of this origin. So the pair will be cancel out each other, means this integral part will be cancel out. So you will find that del x dm equal to 0, and the point for which the integral itself is 0 is the center of mass. Thus the center of mass of a homogeneous thin rod, homogeneous that means the distribution of mass is uniform throughout the rod. So homogeneous thin rod coincide with its geometrical center, and this can be understand on the basis of reflection symmetry here, and with the same method, like means the same symmetry argument will apply to homogeneous rings, disc, spheres, or even rod at the circular or the rectangular cross section. For all such bodies you will realize that for every element dm at a point x, y, z, these are the coordinates at a point, one can always take an element of the same mass at that point, that is minus x, minus y, minus z. As we have taken here, you will find the at the x distance the small element dm, so the minus x distance also the same small element dm can be taken here. The same way for all this geometrical figure, the homogeneous rings, disc and spheres, or even rod of circular or the rectangular cross section, will just find the same point, that is that the same mass at the point minus x, minus y, minus z. So as a result the integral, that is r integral, that is 1 upon m r dm equal to 0, or we can say simply that x equal to integral x equal to 1 upon m integral x dm, y equal to 1 upon m integral y dm, or the z equal to 1 upon m integral z dm equal to 0. So this means that for all the above bodies their center of mass coincide with their geometrical center. Vector product of two vectors or cross product. This already we have learned in mathematical parts, mathematical tools part, but once again we will revise, because we'll learn about the two physical quantities which are the vector product of two vectors, so which is important for further further information of this chapter. So so that we'll revise once again here. Vector product of two vectors a and b is a vector c such that the magnitude of c is given by this way: the magnitude c is equal to ab sine theta, and where a and b are the magnitude of the vector a and b, and theta is the smaller angle between the two vectors. You can see that if a vector A is represented here, B is represented here, and the angle between this theta here, so you will find the resultant of the cross product or the vector product of these two vectors A and B in this direction, that is C, which is equal to A cross B, and the magnitude is given as AB sine theta. Now you will see the C is perpendicular to the plane containing AB. Suppose this AB, the two vectors are in a plane XY, so we'll get the resultant, that is C of this cross product of the two vectors in the Z direction, that will be the perpendicular to the this plane XY plane. Okay, so always we are getting the resultant of the two vectors, the cross product of two vectors or vector product of two vectors, always in a perpendicular to the plane containing vectors. Then direction of C is given by right hand screw rule. As you can see, the right hand screw rule, that means if you just grip this resultant here in the right hand, so where this means the finger curls in that direction, if you are taking the vector like AB, so theta angle we are taking in this way, like anti-clockwise direction, so the resultant will be in the upward. And just opposite here, if we are taking the B cross A, that means the angle theta, this is clockwise direction here, so in such situation you will get the resultant in this direction, and that will be just opposite of the this previous one. Okay, so this way we'll get the resultant in the downward direction. So if the angle is taken here the anti-clockwise, resultant will be upward, and if it is the clockwise, so in that case it will be downward. Now the very important part of the vector is, that means all the laws as commutative rules we have seen. Commutative rules in case of the scalar product we have seen, the two scalar product commutative rules will be followed, but in case of the cross product or the vector product will not follow the commutative rule. That means A cross B is not equal to B cross A, but A cross B is equal to minus B cross A. As you can see here just now, as I told you, the resultant will be in the opposite direction, so this will be the minus C we have written, and this is C. So obviously, and C, and this is minus C, the C vector and the minus C directions are opposite here. Okay, so that we can write A cross B is equal to minus B cross A. Now you will see here in third case you will find that another interesting property of a vector product is its behavior under reflection. Under reflection, that is on taking the mirror image. Like if we are taking here x equal means x the mirror image in the minus x, or y the mirror image in the minus y. So in such situation we'll see that the as a result all the components of vector change sign, so you will get the same resultant. A, the reflection of A is minus A and the reflection of B is minus B. If you are taking the cross product of these reflections, you will get the same result here, that is A cross B here. Okay, this is the third point. Now the fourth point, you will see the distributive law. The distributive law is followed by the cross product as well as the dot product also. So A cross B plus C can be written as A cross B plus A cross C, and we know that the cross product of the same vector will be equal to 0. And why it is 0? Because just now as we have seen that AB sine theta, here we have seen that if it is A cross B is equal to AB sine theta, so if I am just writing A cross A, that means the same vector here, so it is A, this is A multiplied by A, or A square you can say, and sine theta. Theta angle is 0 here, so it is sine 0, and because sine 0 is 0, so the value will be 0 here. So the cross product of same vector will be equal to 0, and so that we are taking the unit vector in the x direction, I, the unit vector in the z direction, j, and the unit vector in the unit vector in the y direction is j, and unit vector in the z direction is k. Okay, so unit vector, that means the magnitude is 1 and the direction in the x, y, or z respectively for I, j, and k. Okay, so if we are taking the unit vectors, cross product of unit vectors, that is I cross I or j cross j or k cross k, that will be also equal to 0, following the same rule as previous one I have explained to you. And if it is I cross j, so these are the perpendicular vectors. I and j are the perpendicular unit vectors, that the angle between them is 90 degree and sine 90 is 1, and I and j is also having the same magnitude, that is 1. So 1 into 1 into 1, that is equal to 1 here. So I cross j and j cross k, k cross I, that all this cross product will be equal to 1. But if you change the order of this cross product, like means j cross I, k cross j, and I cross k, so just following the rule as we have taken a cross b equal to minus b cross a, here if I cross j is equal to 1, so obviously j cross I will be equal to minus 1. So the resultant of all this, j cross I, k cross j, I cross k, equal to minus 1. If two vectors we are representing in the form of, like a, if we are representing axi plus ayj plus azk, and b vector if we are representing in 3 dimension, that is bxi, byj, and bzk, so the resultant of this two vector a cross b will be given by the determinant, that is ijk. This form if we'll write in the form of determinant, so the resultant will be ayBz minus azByi plus azBx minus axBzj plus axby minus aybzk. Okay, so all these properties will use for the vector product of two vectors in this chapter. Okay, the two new physical quantities which we learned. Okay, so we'll find this means all these rules there, we'll just apply all these rules of the vector product of two vectors. Vector products or cross product of some vectors. First we'll see the relation between angular velocity and the linear velocity. Already we have derived the formula for the relation between the angular velocity and the linear velocity in chapter motion in plane. There we have written in the form of magnitude only. Here you will see this is the vector form of the linear velocity, which is equal to, the linear velocity is equal to the cross product of the angular velocity and the radius. Next we'll see the angular acceleration and the linear acceleration, that is the linear acceleration is equal to cross product of the angular acceleration and the radius of the path. Next we'll see the angular momentum. This is the new physical quantity which I was talking there, the new physical quantity that we will learn more in more detail this. So the angular momentum and linear momentum, you will find the angular momentum will be equal to the cross product of the cross product of the radius and the linear momentum here. And the torque, this is also the new physical quantity, and force, the torque is equal to the radius and cross product of radius and the force. So we'll learn about the torque here first, which is also called the moment of force. So we have learned that the moment of rigid body in general is a combination of rotation and the translation. If the body is fixed at a point or along a line, it has only rotational motion, and we know that the force is needed to change the translational state of a body, that is to produce linear acceleration. We may then ask, What is the analog of force in case of rotational motion? To look into the question in a concrete situation, let us take the example of opening and closing of a door. You will find here, you can see a door is a rigid body which can rotate about a fixed vertical axis passing through the hinges. This is the hinge, and here this is the vertical axis which you consider as the rotational axis. Okay, so you will find this door will be rotate about this rotational axis which is passing through the hinge. And what makes the door rotate? It is clear that unless a force is applied, the door does not rotate, but any force does not do the job. A force applied to the hinge line, if you apply the force here in the hinge line, obviously you will find the door cannot be open, means just by applying the force here in the hinge line. Okay, so what you will find is, it is clear that unless a force is applied, the door does not rotate, but any force does not do the job. A force applied to the hinge line cannot produce any rotation at all. Where is a force of given magnitude applied at a right angle to the door at its outer edge from this hinge line, from the rotational axis, if in the perpendicular direction, this is the perpendicular direction from the rotational axis. Okay, so anywhere you will find this. This is the outside of the door, means the edges of the door, you can say. So here if you will apply the force, you will find it can easily open or close. The door can be open and close if you apply the force here, and that's why you find this type of means the support is there to open and the closed door here. Okay, so this is the this will be in the perpendicular direction from the rotational axis. So where is a force of given magnitude applied at right angle to the door at its outer edge is most effective in producing rotation. So it is not the force alone, but how and where the force is applied is important in rotational motion. The rotational analog of force. So what we can say, actually the torque which we just represent with the letter tau. This is the letter tau. Okay, so this is actually the rotational analog of the force. That means whatever the work is doing by the force in the translatory motion, whatever the work is doing by the force in the translatory motion, the same work is doing by the torque in the rotatory motion. Okay, so the force is responsible to produce acceleration. The same way the torque is also responsible to produce the rotation here, the rotational motion. Okay, so the rotational analog of force is moment of force, and it is also referred to as torque or couple, and we shall use words moment of force and torque interchangeably. We shall first define the moment of force for the special case of single particle. Later on, we shall extend the concept of system of particle including rigid bodies. We shall also relate it to change in a state of rotational motion, that is its angular acceleration of rigid body. So here first of all we'll see for the single particle. So if a force acts on a single particle at a point P, you will see that this is the point P which is located here in the YZ plane. Okay, and you will find the position vector of this point P from origin. This is R, and the moment of force acting on the particle here. Okay, the moment of force acting on the particle with respect to the origin O is defined as the vector product of R cross F. That is the vector product of R and F. So this is R cross F, or we can write this tau equal to RF sine theta, or we can write this as FR sine theta. This is the n cap. That means the magnitude of the tau, that is the magnitude of the torque, will be given by RF sine theta, and n vector is representing here the direction of the this is the unit vector, so representing the direction of the torque. So you will see that at this point this is the position vector P, and this is the line of action of the force. You will find this is the line of action of the force. So this is representing, this line is representing R, and this is F, and angle between this is theta here. So this is also theta here. Okay, now you will find that if you just draw perpendicular from this origin here, okay, this is the 90-degree angle. So you will find this is theta, this is 90, obviously it will be 90 minus theta. So if you find this line, this perpendicular line is the r sine theta. Okay, so this is the perpendicular line is the r sine theta. So r sine theta is the perpendicular distance of line of action of force F from origin. So tau can be written as F into r sine theta. The magnitude of tau can be written as F into r sine theta, where r sine theta is the perpendicular distance of line of action of force from origin. Okay, the moment of force has the dimension ml2t minus 2, and it is the same dimension as the work and the energy is there, but this is a different quantity. The tau is a different physical quantity, different from the work and energy. As you know very well, the work is a scalar quantity, energy is a scalar quantity, but we are looking here, the tau is the vector quantity, and tau is 0 if r is 0 or f is 0 or theta, the angle between the r and f will be equal to 0 or 180 degree. Now you will see that in this situation, if the r is equal to 0 or f equal to 0, or if theta is 0 or 180 degree, in this situation you will find the moment of force vanishes if either the magnitude of the force is 0 or if the line of action of the force passes through the origin. One may note that since r cross f is a vector product, properties of vector product of two vector apply to it, and if the direction of f is reversed, the direction of the moment of force is also reversed, and if the direction of both r and f are reversed, the direction of moment of force remain the same.